I think we can start this afternoon session. We will have a prestigious IMS Bernoulli Society Schramm Lecture. This lecture belongs to most recognized because it is supposed to commemorate some really great mathematician that died too early, we can say. As I said, there is a special committee appointing lecturers, and Russell Lyons, today's lecturer, was appointed, I guess, 3 years ago. Could you correct me if I was wrong? If I'm wrong? But of course, pandemic and other circumstances caused that this lecture was postponed. And it is only now that I am pleased to announce this lecture. I would like to introduce our distinguished lecturer, Russell Lyons, obtained his PhD in harmonic analysis at the University of Michigan in 1983. According to his own description, within a few years, some coincidences led him to switch to probability, where he has been happily ever since. Russell Lyons is James Ruddy Professor of Mathematics and Adjunct Professor of Statistics at Indiana University. His primary area of research is discrete probability and its connections to other areas of mathematics, including ergodic theory, geometric group theory, analysis, geometry, and combinatorics. Lyons was a Sloan Foundation Fellow, a visiting Miller Research Professor, an IMS Medallion Lecturer, an invited speaker at the International Congress of Mathematicians, and a Simons Foundation Fellow, and gave an hour address at the joint mathematics meeting. He's a fellow of the American Mathematical Society. Russ, it's time to deliver Schramm Lecture. Please, the podium or the screen is yours.
Thank you, Adam, very much for that kind introduction. And thank you all, whoever is in the audience, for coming. I can't see the audience at all. Hopefully you can hear me well and you can see the screen well, I hope. I am indebted to the committee of the IMS and Bernoulli Society for having invited me to give this lecture. I was a frequent collaborator of Oded Schramm, who was a great mathematician and a wonderful person. And so I'm really happy to be able to perpetuate his memory. If any of you are less familiar with him, I recommend that you do a web search for Oded Schramm Memorial Conference or Oded Schramm Memorial Blog, two separate places where you can find some reminiscences and memories of him and his mathematics. So the picture here on my title slide is based on the IMS logo. I'll explain more about what it shows. So the topic is monotonicity or continuous time random walk. So let me start with continuous time random walk. So here is just a finite graph on 5 vertices, V1 through V5. And on the edges, we have positive numbers. And these represent rates at which the random walk will or can transition from a vertex to a neighboring vertex. For example, at V3, there are Poisson processes of rate 4, 5, and 8 on these edges. And if it's here, then it will cross an edge which is corresponding to a Poisson process which rings at the first time after it arrives here. It crosses it at that time. So because these rates are 4, 5, and 8, the total is 17, and it will leave V3 at rate 17 along the edge that rings first. Okay, so that's just written here on the bottom. These graphs, or with these labels, which we'll call networks, are maybe finite or infinite. They may have structure, they may not. What we will be interested in is varying the rates on the edges and seeing what happens. The idea is that if a rate increases, then the walk will move faster. And so if we have a property of random walk, which is monotone in time, then possibly the property will also be monotone in the rates. However, it's not so simple, because when you increase the rate, you also change the probability of which edge is crossed when you're at one of the endpoints. So the intuition is that it moves faster, but there can be counterintuitive things that happen. So I'm going to provide a survey of the area, just some results that are known, some counterexamples. I will try to give a very brief idea in each case of proofs, and also mention some of the open questions in the area. So that is the goal for my talk. So here's that same network. Now, one thing we want to associate to the network is a matrix called the Graph Laplacian, and in this case, it's over here. So for example, for V3, the vertices, the rows, and the columns are indexed by the vertices, V1 through V5 in order. So for example, in the middle here is V3, V3. And on the diagonal, all we have is the sum of the rates leaving that vertex. Off the diagonal, for example, here, -5, that corresponds to V3 and V2, or V2 and V3. We have -5, which is negative of the rate of that edge. So because of the way this is set up, all the row sums are 0, and it's a symmetric matrix. So that is the Laplacian matrix, which we will see is how that's related to this random walk. So here in brown, I just repeated what I said. So how is it related to the random walk? Well, negative of the Laplacian is the infinitesimal generator of this continuous time Markov chain. And what does that mean? It means that if we want to know the transition probability p sub t of x, y, meaning if we're at x at a given time, question is, what's the probability of being at y a time t later? We take the matrix exponential of e to the minus t delta, that infinite series, and look at the x, y entry. So that means we take this matrix, multiply by the vector, which is 1 at y and 0 elsewhere, and take the inner product with the vector, which is 1 at x and 0 elsewhere. Now, I claim the stationary distribution is always the uniform distribution. So why is that? Well, intuitively, because the rates are symmetric, if we put a uniform distribution on the vertices, the amount of mass that crosses an edge is equal in both directions for every edge. And so the uniform distribution is preserved. Algebraically, by the way, I hear a little bit of an echo, which I'm presuming you are hearing. I hope you don't hear the echo, but I think I'm hearing the sound of the speakers. Hopefully it's not disturbing you. So algebraically, 1 is an eigenvector of the Laplacian. That's because the row sums are 0. The eigenvalue is 0. And so therefore, 1 is an eigenvector. This is the constant function 1 of e to the minus t delta with eigenvalue 1, e to the 0. So let me begin with a couple of well-known properties. First, the Laplacian matrix is a positive semi-indefinite matrix. So let me just sketch the idea. Each edge corresponds to affecting 4 entries, 2 on the diagonal corresponding to the endpoints and 2 off the diagonal. And what we have for those 4 entries is a multiple of this matrix, 1, -1, -1, 1, where the multiple is just the rate on that edge. And this little 2 by 2 matrix is positive semi-definite. And so we just add up these 2 by 2 matrices in different places. And so the sum is positive semi-definite. Now here's a corollary of that property. The return probabilities are monotone decreasing in time. So why is that? Here's a sketch. Well, because Laplacian is positive semi-definite, the eigenvalues and I are non-negative. So if Fi is a set of orthonormal eigenvectors of the Laplacian, we can compute the return probability by this formula and expand 1 sub x in the basis of orthonormal eigenvectors, and it turns out you'll get this. So everything is non-negative. Lambda I appears in the exponent with the minus sign. And so if we increase t, it decreases, and it decreases the return probabilities. So here's a simple example of a network with 4 vertices, and you see the 4 return probabilities graphed at time, just going from 0 to 2. They all approach 1/4. The uniform distribution as time tends to infinity. The one which is decreasing fastest at time 0 is this dark blue one, because it leaves this vertex at rate 13, and everything is probably 1 at time 0. Now, so now that we have this monotonicity in time, remember our theme was, what about monotonicity in the rates? If we change these rates, what will that do to the return probabilities? Well, notice one simple case. Suppose we multiply all the rates by constant. That's equivalent to multiplying time by that same constant. And we know we have monotonicity in time, and so we would have monotonicity in that simple case. But what about in the individual rates? For example, suppose we just concentrate on the middle rate, rho. If we increase rho, what does that do to the return probabilities? So let's fix a time, say time 1. What will it do? Well, there's 4 return probabilities we can ask about for the 4 different vertices where we increase rho. And I will tell you that actually all 4 are monotone in time except for 1. If we had more time, I'd let you try to guess which one that is, but actually there's no real intuition that I know of. It turns out this light green one, the green one, this second one over here, is not monotone. So here's rho. 3 is where we were at before. That's this dashed line. Time is 1. And I just started from rho equals 1 to 20. And you can see that these 3 are monotone, but this other one is not. So that's too bad. Counterintuitive. However, suppose we look at the average of those 4 return probabilities. Here it is. It's monotone. Is this just a coincidence? Actually, it is not. This is a result of Benjamini and Schramm. On every finite graph, the average return probability at every time is monotone decreasing in the rate function. So here's a sketch of the proof. Suppose I have 2 rate functions, r and r prime, and r prime is at least r everywhere. Remember how we computed this Laplacian? We added the rates times these little 2 by 2s, and so the r prime is a bigger Laplacian. And as a general fact, if I have a bigger matrix, all the eigenvalues go up. Now the sum of the return probabilities is the trace, by definition of trace, sum of the diagonal elements. But we can also compute the trace using the eigenvalues, which is this. So if the eigenvalues go up, the sum goes down, and so the average goes down. Now, here's an interesting thing. The average return probability, we're just taking this trace and dividing by the number of vertices. I will denote this with a capital T and normalized chart. Suppose we're in the following situation. Suppose G is vertex transitive, meaning it looks the same from every vertex as any other. More explicitly, given any pair of vertices, there's a bijection of the vertex set, which takes the first to the second. It preserves all adjacency, and it preserves all the rates. So that would mean this average is the same everywhere. It's just one, take any vertex, oh, it's just return probability. And the interesting thing is this makes sense on an infinite graph that's transitive, which actually leads to an open question. Suppose G is an infinite transitive graph. Is the return probability at a vertex as a function of the rates monotone decrease among transitive rate functions? Well, there are things that are known about this. But first, let me just give you some examples of graphs where we might want to look at this question. This one's finite, but this will come up later too. This is a Cayley diagram, which I'll explain what that is in a moment, of the symmetric group on the numbers 1 through 4. So for example, here's the two permutations 1, 3, 4, 2, 3, 1, 4, 2, and they're joined by an edge here, which is transposition of the first two numbers. We switched the first two, which in this case are 1 and 3. And so this is the graph of all 24 permutations connected by adjacent transpositions. So what do we mean by Cayley diagram? We have a group which is generated by some subset S, which means that the smallest subgroup containing S is all of gamma. Then first of all, the corresponding Cayley graph has vertex set, which is the group elements, and edges where you multiply on the right by a generator. That's the graph. If we label such an edge by the generator S, we get what's called the Cayley diagram. So over here, it was, I used the colors with this key down here to get the Cayley diagram. Now notice the following fact. If xs is an edge, and we multiply on the left by any group element gamma, this is also an edge. And because this is a group, gamma is acting transitively on the Cayley diagram. You can get from any vertex to any other. When is the rate function transitive? If and only if the rate depends only on the label, the generator, and not on the endpoints, specific endpoint. And we're only considering symmetric rate functions. So if S is not the same as S inverse, then this rate function is the same as a function of the generators to be transitive. Now here's an infinite case, which would be illustrating the question that I asked before. In this case, there are three generators, A, B, C, and they're all involutions, but there are no other relations. So this is a presentation generated in this way. So we get a tree. There are no cycles. And it's a free product of three copies of Z-mod 2Z. So of course, this goes on forever. Okay, I said there were some things that were known about that question. So here's the first theorem, due to Brown, that in the case of a Cayley graph, if we look at transitive rate functions, then we do have the monotonicity that we asked about. If we increase the rates, the return probability goes down. And here's this very brief idea of the proof. We do use a trace, but it's this normalized trace, and it's just defined by looking at this particular, any one of these diagonal elements, or so-called equivariant operators. So you can prove, it's not hard, that this is a normalized trace, which means it has the properties you're used to for a trace, which were listed here. And then you can use this to give a proof. Well, there is an open question related to this. Suppose we look at random rate functions. So they're no longer invariant, but the law is invariant. So it's a random field. So at every edge, we have this RG is less than or equal to R prime, but the laws of RG and R prime are invariant under that multiplication. The question is, do we have the same kind of monotonicity? This is open even on regular trees. But there are some things that are known. In fact, Fontes and Machio proved the first such theorem that this is true for an amenable Cayley graph. Amenable is like Z to the D, where there are sets, finite sets whose boundary is arbitrarily small compared to the size of the set. So they proved you do have this monotonicity. With David Aldous, I extended this, replacing this amenable assumption, getting rid of that, and instead with this other assumption, where we require that the law of the pair R prime is invariant. And it's easy to prove that in the mutable setting, you can always couple it, so this is true. So it is an extension. And the proof is similar, that for equivariant random operators, you can also define a trace by taking this expectation. Okay, there are three basic sections of this talk, and this is the end of the first one. We have return probabilities. Lots more one can say, but this is just a survey. So let me turn to a different topic, a monotonicity in distance. First, let's ask about time. So d of xy denotes the graph distance between two vertices in a graph. And suppose we're talking about this same continuous time random walk. And now let's look at the expected distance as a function of time. Intuitively, that should increase. But does it? Well, actually, no. In fact, Oded provided a very nice counterexample illustrated here. Consider a cycle on a large number of vertices, and we have rate 1 on each edge on the cycle. These are in brown here. Then we're going to add new edges of a very tiny rate, 2 to the minus n, between each pair of vertices whose cycle distance is at least square root of n. Now, what's happening? Suppose you look at time n to the 1/3. How far is the walker likely to be from its starting place? Well, it's very unlikely to take one of these new edges because the rate is so small. So it's basically just walking on the cycle. And we know it's going to be a distance around n to the 1/6 in the cycle distance. But what is that distance with these new edges? It's 2, right? Because you can go far away and then back. Now let's look at another time, n squared. Well, it's again unlikely to have taken any of these tiny rate edges. Now it's more or less uniformly spread over the cycle. And what distance is that? Well, probably just 1, connected by one of these new edges. So we see that as time has increased, the distance has gone down. And this is a very nice setting. It's a Cayley graph with transitive rates. So things aren't so good. However, Mark Rauterman observed that you have near distance monotonicity in very general setting, any finite network, if you start with a uniform vertex. Well, I wrote down the monotonicity that we don't have, but he proved that if we just put in a little factor of 2, then it's true. And the example we just looked at shows that 2 is sharp. So this raises an open question. Now that we have near distance monotonicity, time, what about in rates? If we just increase the rates, the same setting, is there some constant that will give us monotonicity? This is open even in the transitive setting. So now I'm going to slightly change the topic, something very closely related to this, but moving from the finite to the infinite. So going back to this, I'll start with this example of a three-regular tree. And then we start with just discrete time, simple random walk, just to start things off. So at every vertex, it just chooses one of the 3 neighbors with equal probability and crosses. What we want to look at is a limiting speed. So after many, many steps, how far is the random walk? Divide by the number of steps, which is time, and take a limit. So for discrete time random walk, what will that be? Well, at every vertex except the starting place, there's 2/3 chance to increase the distance by 1 and 1/3 chance to decrease the distance by 1. So the drift is 2/3 minus 1/3 or 1/3, and that will be the limiting speed. All right, but we were interested in continuous time random walk, so let's start with the simplest case. All the rates are 1. So what will the speed be now? Well, it's just doing simple random walk, but it's making a transition, it's leaving a vertex at rate 3. So it's 3 times 1/3, which is 1. Okay. Now, let's suppose we have general rates depending on the generators. this nice transitive situation. And this just changed one of them. So two of the rates will be 1, but one of them will be rho. Because everything is symmetric here, it doesn't matter which one we take. Say this dark red one. If rho is 1, the speed is 1. Suppose we take rho to 0. What will the speed be? Well, if the rate on an edge is 0, that's like deleting that edge. It can't cross it. So if we delete all these dark red edges, all we have left is this green and blue edges, which just form like a copy of Z, a bunch of copies of Z. Whichever one we start on, it'll be restricted to walking on that. That speed is 0. Like simple random walk at rate 2. Okay. So let's look at the opposite extreme, where rho is tending to infinity. What will the speed approach now? Well, this is hard to understand. That means it's going back and forth across this edge very, very fast. But at rate 2, it will leave this edge. No matter where it is, at rate 2, it will take one of these other edges. So it takes a while to figure this out, but it turns out it approaches 5/3. So we have 3 data points here in this monotonicity question. 0 when rho is 0, 1 when rho is 1, and 5/3 when rho is infinity. So that's monotone. But is it actually monotone for all rho? So let's look at an intuition here. What is happening when we're increasing rho on all these red edges? Well, that means whenever we're at an endpoint of a red edge, which we're always at an endpoint of a red edge, we're going to cross that edge more likely and quicker. Now, if we're at an endpoint that's closer to our starting point, that's good, because then we move away faster. On the other hand, if we're at the other endpoint that's further, then that's bad because we move closer to the starting point, more likely and faster. So there's this trade-off. And intuitively, and with these this evidence, it seems like the monotonicity increasing wins. Does it? Well, it turns out you can calculate. And here's the formula. Now, if you look at this formula, actually, it's not obvious what's happening, but it turns out it is increasing. Well, that's not so enlightening. Is there a good reason for being increasing? So we could ask these questions. Suppose all 3 rates are different. Is the speed increasing in each rate? What if the degree of the tree is more than 3? What if we look at other Cayley graphs with symmetric rates on the generators? Well, one case again is easy. Increase all rates by the same factor. As we saw before, that's equivalent to increasing time by that factor. But that increases the speed by that factor. This is because we're taking a limit, unlike that finite case before where we did not have distant monotonicity in time. Here we do. We have monotonicity trivial. All right, so that's good. That means this question is a reasonable question to answer. So what are some other examples where we would put this question besides regular tree? So here is, again, a picture based on the IMS logo, not the one from the title slide, where the symmetry group is one whose Cayley gives a Cayley graph that we might want to examine. So first, let me say, what is the symmetry group? Where did this picture come from? Well, there is this triangular tessellation of hyperbolic disk. Here's a fundamental triangle. The sides are geodesics, the hyperbolic metric, and we just reflect this triangle over and over again to get this nice tessellation. So I take this tiny portion of the IMS logo right here, and I reflect it in these triangles, and that gave me the picture I started with. So the symmetries exist. So the white line geodesics that we had before. And in the colored edges, in brown, blue, and red, we have the Cayley diagram. So there's 3 possible reflections each time. So A, B, and C, they're reflections, so they're involutions. And we also have these other relations. So for example, AB gives you this quadrilateral. BC cubed gives you this hexagon, and CA to the 7th gives you this 14gon. And that turns out to give the group. This is called the 2, 3, 7 triangle group. So this is obviously much more complicated than the tree, right? It's true you move closer or further when you and faster when you change your rate, but the moving around in different places really makes things more complicated. Now, we were looking, the question asked was finding a good reason for being monotone and how general that is. So one natural approach would be to say, if I have 2 of these random walks, one has higher rates than the other, can we couple them so that the more active one, the one with higher rates, is always at least as far from the initial position as the other one? If we could, that would be a great theorem, and hopefully would and ought to provide a lot of understanding. Well, it turns out you cannot do that even in the simplest case, even in this case of a 3-regular tree, even when 2 of the rates are 0. So what does that mean if 2 rates are 0? Well, then the walk is just moving back and forth across one edge. So think about it. Suppose I have a slow rate and a fast rate. One of them is moving back and forth very fast, and the other was hardly moving back and forth at all. How can you keep the faster one always at least as far as the slower one? So it'd be intuitive, that's impossible. And you may object, that's a very degenerate case, not very interesting, but actually you can choose times and rates that make the situation we just described essentially the same when even all 3 rates are positive. So coupling is out, even in a case where we think monotonicity might be true. Well, actually, in general, it turns out monotonicity is not true, even in this, and here's a counterexample that's very much like a tree. We take Oded's counterexample here, and that was a cyclic group with some extra generators, and we take a free product with Z mod 2. So that means you stick on extra edges, and on the other side of this edge, you put another copy of the same cyclic group, and so on forever. And then it's not too hard to check that if you increase rates in these big cyclic groups, you can actually decrease the limiting speed. So there's very simple examples where we do not have monotonicity. Okay. So what about trees, though, where it seemed like maybe we do? Well, it turns out actually we do, and this is proved in joint with Graham White. In that example we started out, we do have monotonicity that's in accord with our intuition in general. And in fact, the proof uses coupling, even though the best kind of coupling is impossible, even in this situation, as we saw. So I'll just give you a very brief idea of 2 ingredients in the proof. One is we need some extra flexibility for our coupling. And that's using the following traditional idea. Instead of using Poisson clocks with grade rho, we double the rate. But when this clock rings, you flip a coin to decide whether the walker will cross the edge or not. So this extra coin flips gives you some extra flexibility for the coupling. And I will just tell you one step in our proof. Remember, for the tree, the intuition was pretty clear. If you're at the closer point of an edge and you increase the rate, it's good because you move away faster. But at the farther end point, it was bad. Well, it turns out that in this situation, we have 2 adjacent vertices, W and W prime, that in this general situation, at any time, the random walk is actually more likely to be at the closer point than the further point. So that sounds good, and it is good, in fact, to say that increasing the rate should Step one is proved with coupling. And I don't have time to give any details, but in this edge, there's a certain reflection that you can do that makes it work. So I will just say that about the proof. But that idea of reflection, in fact, extends quite a bit to the Cayley graphs, all Coxeter systems. So the example of a tree is a Coxeter system. The 237 triangle group is a Coxeter system. These three here are finite ones, which will come up more in the rest of the talk. The one I showed you so far was this one at the bottom, symmetric group generated by adjacent transpositions. That's another example of a Coxeter system. Dihedral groups, which I'll show you pictures of, and 235 triangle group, which I'll show you again. So I don't have time to give you the definition, but let me just say that it's defined by certain presentations, and these are all examples, and that the Coxeter groups are abstractions of reflection groups. So there is an open question related to this, similar to one we looked at before. Suppose you have random fields of rates on a Coxeter system, where the first is the most the second, almost surely, and the laws of the fields are invariant, is the expected speed of the first at most out of the second. And that's open even on regular trees. So that's the end of the second topic. And now on to the third and last. This will be about finite graphs, but as time tends to infinity. Now, as time tends to infinity, of course, the distribution of the random walk tends to the stationary distribution, which we saw was uniform. So having heard the previous result of mine with Graham White, graduate student Yiping Hu asked, does increasing a generator rate decrease the distance to the uniform distribution? So where might we be interested particularly in this kind of a question? So here is the picture on the title slide. The symmetry group of this is an interesting example. And what is this? So now you might be expecting this. This is a tessellation of the sphere based on reflecting, again, triangles. And we take a portion and reflect it on the sphere. So here is the Cayley diagram. And there are quadrilaterals, hexagons, and tangons. Here's a much more beautiful picture showing you the whole Cayley graph. And that's his presentation, which I gave you an example before. So this is a Coxeter system. And here's the one I showed you before for the symmetric group on 4 letters. And here's the dihedral group. It was very boring as a graph, but nevertheless, not all questions are obvious to answer for random walks. Okay, so here is Yiping's question again. But we need to say, what do we mean by distance? We could measure distance in various ways. For example, we could use LP distance or relative entropy or other natural distances. So here are some observations. First, on any finite group, if we increase time, then we will decrease the distance to the uniform distribution. And therefore, it definitely makes sense to ask about a similar increase the rates. Well, actually, a very similar proof will show that if we have an abelian finite group and we increase the rates, that will decrease distance to the uniform. On any finite group, if we use the L2 or L infinity distance, we will decrease the rate, the distance to the uniform. And with Graham White, we proved that on any finite Coxeter system, actually, at any time, increasing the rates decreases the distance to uniform in all natural senses. Now, what do we mean by all? Well, So here's an idea of proof. We actually, turns out you decrease the distribution itself in the majorization order. We again use reflections, and that's why it works on Coxeter systems. So it's not always true, however. In fact, even in a Coxeter group, if we change the generators from the one that gives us the Coxeter system presentation, we may actually increase the distance to the uniform at certain times and for certain sets of rates. And here are some examples. Let me concentrate on the three highlighted ones in the middle. These are all for dihedral groups. Remember, for any group, any generator set, L2 distance and L infinity distance, we will always decrease the distance to uniform when we increase the rates. However, we could find counterexamples for P between 1 and very, very close to 2, and P very close to 2 above and up to very close to 4. And then very close to 4 on the other side and up to close to 6. So the fact that we could do these near 2 but not at 2 is not so surprising. But we could never find an example at 4 or any P at least 6 for dihedral groups. We have no idea why not. And so there's definitely something to explain. Either it's actually impossible, and we would have no idea why that would be. Or it is possible, but it's extremely rare to find such behavior, and we also don't know why, but that would be very interesting to explain if that were true. Lastly, this other example here was entropy, relative entropy, which is actually contrary to conjecture that I made in 1999 with Benjamin and Schramm. Let me talk a little bit more about that. In that case, in all these cases, we have found only barely counterintuitive behavior. And so it makes sense to ask about near monotonicity. For example, we could slightly modify the conjecture of Benjamin that I made with Benjamin and Schramm to the following. And this is actually this is beyond Cayley graphs to all finite graphs, any two rate function. And let's say D is relative entropy. We'll measure distance in relative entropy, fix some time. Look at the distance to the uniform, law of xt, given that we have a certain starting point x. And now average over the starting points, like we did at the beginning of the talk for return probabilities. And compare that when we increase the rates from R to R prime. If this constant were 1, that would say we have monotonicity. We know we don't have that in the transitive setting. But is there a constant such that we do have this always? And it seems likely that this is true, even for C close to 1. But for any positive C, this would actually be enough for the purposes for which we made our conjecture. So this is a very interesting open question. And I will stop here, and thank you very much for your attention.
Thank you very much for very instructive, clear, and full of open questions talk. I haven't heard about so many questions open in one talk. It's really impressive. Are there any questions? Please.
I can't hear anything. You'll have to repeat the question.
Oh, there will be a question. There will be a question.
Okay.
No? Or not? Okay. It seems it's too far. Okay, please ask question. You can.
Hi. So this one, okay. Okay. So the question is, have you thought of if you can induce or consider a partial order in the graph and then answer these questions about monotonicity using ideas of stochastic comparison or stochastic dominance?
I'm not sure what you mean by introducing order. So we do use an order, especially in the last topic, which is called the Bruchot order, in a special case of Coxeter system. So there's a natural order agreeing with that. But are you asking about something general instead of whether something's true, or are you asking about a proof method? I didn't really understand.
It's just that I'm curious because if you consider, let's say, a partial order in the set of vertices for the first two questions, I think, then some monotonicity is equivalent to the existence of a coupling. So yeah, I don't know if then there's no a possible partial order in the vertices that could answer the first two questions.
Well, I'm not sure I understand the question, but in any case, I think even if I did, I wouldn't know the answer because, you know, I showed you certain things are impossible. Even though we used coupling, and we use coupling in that case as well, one has to be very, very careful how one does that coupling, because in fact, you cannot construct a coupling that does everything you want for all time. You have to put together various couplings that each one does a nice thing in a certain portion of the time, but not at other times.
Okay, I understand. Thank you.
Okay.
Thank you. I think we have no time. Thank you once again, Ross, for perfect lecture. Thank you.